So today we're in 5.6 doing a thing called integration by substitution. Basically, this exists to do the chain rule backwards. So when you've got like pretty big, long, complicated derivatives, like if I asked you to do the derivative of this, we've done the chain rule where you work from the outside in. So just recapping that, if we had to do the derivative of this, we'd worry about the fifth power first. So we'd go 5, copy the stuff to the fourth. Then we would do the derivative of the inside, which is a 3, and we'd multiply the 3 onto the 5 we already had, so we'd have 15 d's to the fourth. We're trying to now go opposite of that. So we're trying to do the chain rule backward. A technique that got invented over time is a thing called integration by substitution. So I'm not sure why they chose the letter U, but the official math letter of substitution always seems to be U. Don't know. Just is. Algebra 2 did that some, this book does that a good bit. So what we're going to do is we're going to pick out a U, which will be some sort of a bite-sized chunk. Don't try to pick something that's the whole problem, that's too much. If we could do the whole problem, we wouldn't be doing this substitution thing. We're going to try to pick out some little bit bite-sized piece, probably in parentheses, maybe it's under a root, something like that, that's what we're looking for. So this, I picked my U to be 3x plus 2. Then we're going to have to compute a thing called a differential, a derivative, figure out the derivative of U. The derivative of this would be 3, and since I did an x derivative, I'm going to put dx. The derivative of this would just vanish, so I'm not worried about that. Then I look back at the problem and everything gets a new name. I'm going to get a new integral with new names. 3x plus 2 was just given a new name, which is U. This used to be to the fifth. This is now called U, but it is still to the fifth. And I want to look around and hopefully see this as well. I don't quite see this. I see something close to it, but not quite. So sometimes there's a compensation and an adjustment to make here. Okay, I need to find a 3 dx. I only have a dx. So I'm going to need to insert a 3. And you know full well by now you can't in math just start sticking stuff in unless you pay for it. If you're going to put in a 3, what can pay for that is a 1/3. That evens life out. 1/3 times 3, it's really like it's not even there, but we need it to be there to make this substitution. 3 dx has a new name, which is du, and this 1/3 was our payment that comes along with us for the ride. Now this isn't nearly as scary looking. That's a pretty basic looking antiderivative problem. So u to the fifth would rise up to be u to the sixth. We would need a 1/6 for that. The 1/3 is still waiting there for us. The grand total of this is 1/18. But instead of u to the sixth, we want to get everything back to its original name. We want an answer that's suitable for this style of a thing. So the u gets reintroduced as 3x plus 2 to the sixth with our good friend, the plus c. If you wanted to check this, you would do it with the derivative and the chain rule. So the derivative with the chain rule would bring down the 6, so 6/18 or a third, stuff to the fifth. Derivative of the stuff would be a 3 to kill the 1/3. We wouldn't have a number at all, like we didn't want to, stuff to the fifth. The derivative of this is this. We've done the chain rule. Problems are all the same. In style, in the sense, you'll always pick a u. You'll always find a du. You hope that the du is there, but sometimes it isn't, and you've got to fix it and pay for it. Do a rewrite where the problem is much simpler. Do the antiderivative, trade back. So here we go again. So this one up, we need to pick a u. Don't get too greedy. Okay? You don't want to pick the u to be like, let's say, this entire root. That's too hard. We want to pick something that the derivative will be easy to do. So something like 1 plus y squared. That's a nice little bite. Okay? You don't want a giant feast worth of math. You just want a bite of math. So 1 plus y squared would be a good pick for the u. The du would then be a 2y, and I'll throw a dy on there this time because I did a y derivative. And then I look for these things and see what their new names should be. So this time, this is a perfect match for that. So this vanishes, it's renamed du. This was called u, but it's under a root, so let's call that u to the half. And now we have a much simpler antiderivative to do. Power rises by 1 to 3 halves. Divide by that new power, so 2/3. And then for our best final answer, it's going to be 2/3 stuff to the 3 halves. And don't forget our friend the plus c. But instead of u, we want to reintroduce the 1 plus y squared. This one, same kind of thing. Pick the u, and if you think you've got it, pause the video and do it yourself, and then you can play along with my answer after you unpause. The u would be 4t minus 1. The du would be a 4 with a dt. So insert a 4 to produce that match and pay with a 1/4. New problem would be a 4th. This was basically why we picked u, but it's to the half because of the root, and du is present. It's the same antiderivative we just did, so I'll just refer back to that one. We just have 1/4 multiplying 2/3. 1/4 times 2/3 is 2/12 or a 1/6. And we'd be to the 3 halves like we were a minute ago, plus c like we were a minute ago. Just our u this time was 4t minus 1. This one, just pick the u to be 7 theta plus 5. The du would be a 7. And a d theta, because we did the derivative of theta. Search for this, sort of find it, but short of 7. So a 1/7. So our new problem is a 7th integral cosine u du. So the answer will still have a 7th. It'll have the plus c. And we just have to think about what is the antiderivative of cosine. Antiderivative of cosine is regular sine without the sign change. And I could do a u for a second and then replace it, but I might as well just replace it while it's fresh on my mind. And then we're good. For this one, you got a couple choices, I guess. I mean, you could look at the x squared maybe to be the u. You could look at the x cubed maybe to be the u. What I'd look for would be like, do you have any invisible parentheses? Trig arguments always have invisible parentheses. Your calculator makes them visible for you every time you hit a trig button. So the u is generally found either in parentheses or in a root somewhere. So u would be x cubed. The derivative of u is 3x squared with a dx. So here's a dx. Here's some of the x squared-y stuff. We're short to 3. So to make this match, since we're short to 3, go a 1/3. So a new simpler problem will have a 1/3. It still has sign. The parentheses got renamed u. And du is there. And that's simple antiderivative time. 1/3. The antiderivative of sine is negative cosine. And instead of writing a u, I'm just going to bring back that x cubed plus c. And we're good. This one, instinctively, I just see that and think I need to do a trig trick. I'm not sure how to explain to you where that comes from, other than like fractions with cosine on the bottom are generally not your friends. If we try to integrate a fraction, that's more of a pain than if we didn't have a fraction. The first thing you want to do on this is trade cosine stuff for secant stuff. Cosine flipped is secant. It's still squared because that's squared. 2 theta still there, d theta still there. This is a less attractive problem than this, because if we go to look at our card for integral of secant squared, we have it. The integral of secant squared is 10. But I should pick my u first. I'm getting a little too carried away with myself. Rewind. I need to pick a u. My u would be 2 theta. My du would be just a 2 with a d theta. When I look for this, it's not quite all here. I'm short the 2. so I need a half. So my simpler problem is half integral secant squared u du, which will be half. The antiderivative of secant squared, if you forget it or if you don't believe me, we had a table of integrals back here on 314. 314, the integral of secant squared is tan. I could put a u for now to hold place, but in the long term, I don't want the u. I want the u traded back for the 2 theta, parentheses if you like them, plus c. Quick check on my board to make sure I'm continuing to get my plus c's. I did. I'm 6 for 6 on plus c's. But sometimes you forget, and sometimes you hit that moment where you're like, wait, did I get them all? Maybe do a quick look back through, make sure you're doing them. This, we've got 2 things in parentheses, so if you're not sure which one you want to do, I guess there's 2 giveaways on this. One, we want this to be the u because it's the one going to a power. We also want this one to be the u because if we do the derivative of this, it sort of looks like that. But if we do the derivative of this, it doesn't look at all like that. Okay, so if you have 2 things and you're not sure what to do, is one maybe the derivative of the other one? Or maybe does one have a power? Maybe that's some good tips. But the u is going to be this part of it. The du would be 2x plus 2, and that would all have a dx with it, so I'll wrap that up in parentheses. And if I look for this, it's kind of there. If I would distribute a 2, I'd have it. And I will, and I'll pay for that with a half. So my new question would be half integral. This is renamed u squared, and all the rest of that mess is du. And that's a nice, simple looking integration problem now. U rises to 3 with a 1/3. The half is hanging out there. So grand total would be a 1/6. We're cubed, bringing the cube along, and just get the u back in there, plus a c. This one, the u needs to be one of the trig things, and so I'd go back to my tip from up there. I'm going to pick u to be sine because the sine is the one going to a power. The derivative of sine is cosine, and I'll throw a dt on there. So this is found perfectly. That's du. This integral has sine to the 4th. Sine was renamed u, so u to the 4th. And then antiderivative time, rise to 5, a 1/5. Grand total, 1/5. U was sine to the 5th, t, all c. One more, then I'm out of examples and out of room. So on this one, I'd pick the u to be the thing that's under the root, which is z squared plus 1. du would be 2z, but with a dz. If I look for 2z dz, there it is, so that's beautiful. So this new integration problem has the du accounted for. This u is right here. It's on the bottom, so that's a negative power. It's rooted, so that's a half power. Antiderivative of this easier problem, we raise the power by 1 up to a positive a half. We always divide by the new power. Dividing by a fraction flips it, so there's a 2. So the grand total answer on this would be 2. The u was z squared plus 1. You could either go in parentheses to the half, or even just I'll bring the root back, because half power means root, plus c. And that's what we're doing. So again, a summary. You look at the problem, you look for something that's a comfortable, nice, small size that you'd be willing to do a derivative of without really any hassle. Pick that thing to be a u. Find its derivative would be a du. Look around for the du. If it's there, great, move forward. If it's not, you're going to have to maybe make adjustments with numbers, like 5s versus 1/5. Make a renamed problem that should be much simpler looking than you originally came in on. It'll have u's and du's. these du things are always just kind of decorative. Like we had those dx's for a while, they didn't really do anything. They just disappeared when you do the integral. But we have them, they're there. Do an antiderivative, just make sure you replace the u back in, throw plus c on. It's our scheme. So, see you next week.